Swayam Prabha. Digital India. Educated India.
ஒரு நிமிஷம் கொடுங்க. நாய்ஸ் பாருங்க. எப்படி ஓகேங்க ப்ளீடில்
This is the mic?
கேமரா டேரக்ட்.
Okay. So should I keep this also? Yeah. Okay. So good evening everyone. This is for the inquiring if my application was received. And the reply came immediately and Sati told me, a decision has been made but I am not supposed to tell you. So wait for an email. And the email did come on Monday and that really started my career in India. So thank you Sati for bringing me to India. And another interesting thing I remember is that after this offer and before I returned to India, I had another email exchange with Sati. I don't remember the details, but his reply again came immediately. He was planning to come to US, but I realized we couldn't meet. But what the email had was really interesting. I planned to go to Salem from Kanpur, attend some functions, spend some time with family, then go to US, attend a conference, and return to IITK before the semester begins. I thought, my God, I would love to do this. I'm glad I was lucky to do. In fact, I reached IIT Kanpur on 6 November 1994. Sushanta was there in the train station to receive me. Those days, he couldn't think about flying. So I spent 1.5 days going from Madras and Sushanta came to pick me up. On reaching the campus, I headed to Sati's house for lunch. Had a great time there for 5 semesters. Sati, Tapas, Amalindu and Srigari. We used to have regular group meetings and we had a lot of discussions. And I do remember Suguna and I won a quiz on old Tamil songs conducted by Tamil Peroi there. But what's really interesting or very important is being a director of IISc Mohali and really changing the science education and research in India. Because he did write a book about this and I got a copy of this. This is something everybody would know. Sati was the director, one of the 5 directors initially. But something that many may not know is the JAM examination, Joint Admission Test for Master's Vision. When I got admission in IIT Madras in 1982, IIT Madras had an entrance exam. Every IIT had an entrance exam. And we had really, I don't know, tens or hundreds of entrance exams. I hope I am not mistaken, Sati can correct me. I heard that Satyamurthy and MS Gopinathan from IIT Madras thought we should have entrance exam together. And that may have been the origin of JAM. So thanks Sati again. Before Supreme Court forced us to do that, we got rid of some entrance exam. What's really interesting, I became the integrated PhD coordinator. Until then, IISc was not joining JAM. I ensured that IISc also joins. So, thank you. Of course, just as I was coming to Pondicherry, I had a message from Vinayak Sinha. He keeps writing to me now and then. I was chatting with him about his results and suddenly I told him, you know what, I am going to a conference to felicitate Satyamurthy. Then he said, can I send you a slide? I said, please do. And this is what Vinayak Sinha says. Every year on the day of Diwali, day after Diwali, you have sent warm replies to my email that shares data from the blue eye in the sky set up during your tenure at IISc Mohali. This for us is a personal reminder of how much your heart continues to beat for IISc Mohali. Thank you. And this is from Vinayak and Birbal Sinha. Happy 75th years on planet Earth, Sati. Here is wishing you many more years filled with good health, exciting science, fun moments, grandchildren and family. Friends, colleagues, have touched so many lives. I together assembled a bunch to build IISc Mohali and your legacy is forever in the history of Indian science. Countless sacrifices and tears of both joy and anguish were for the course. Hope you enjoy peace and fulfillment in your current and second innings. So, this is from IISc Mohali. Let me now begin my talk. I have told the organizers I'll spend the first few minutes and I will not come again when Sati is being felicitated. So, I have taken that time. So, chemical kinetics. One can never say never is a popular movie by James Bond. But this is really applicable. One can never say a mechanism is correct. One can, however, disprove a reaction mechanism. This is from Urbana-Champagne course I downloaded. This statement is about a complex reaction, but advances in experimental theoretical methods are making it applicable even for an elementary reactions. As we saw even in this do meeting, sometimes atoms decide to roam rather than crossing a barrier. So we established a single pulse shock tube for investigations on fundamental chemicals in 1997. It's been used for pyrolysis, combustion, ignition related measurements over the last 28 years. Now this talk is about astrophysics. It's a brief outline of my talk. Introduction to shock tube as a laboratory tool for astrophysics. Inverse of soot formation, C plus H2 reactions. Time resolved spectroscopy for shock tube. C60 pyrolysis, current development, C2 vibronic energy levels, reaction mechanisms. I did talk some of this in the ICOMET meeting Lurdraj organized years ago. Shock processing of coronium is something it's just been accepted. I will mention some of it now. And C2 plus C2 reaction, I would certainly like to have a few minutes at the end in case I exceed. Thanks to my colleague Mapudi who did not come, I think I can take some more time. Conclusions. So in 1997, we started two 1997. So I'm not going to talk about microspectroscopy, but I'm mentioning this because of a reason. So we built this spectrometer because we worked on H2S. Eventually could convince IUPAC to change the definition of hydrogen bond. But we had this lab with Prof. KPJ Reddy and my first student Rajkumar. He had joined my lab and I didn't have money to build a spectrometer yet. And the shock tube was available, we started working. And I couldn't imagine what has happened. This is a more recent photograph. This is our laboratory looks. I invite all of you. This is Ludovic Bainier, Samir Kasi from Grenoble, Robert George, Jagadish and Deepak. We've been doing some astrophysics work recently. You know, in 2004, Bertrand Rowe from University of Rennes sent me an email. He developed this technique, CRUSU. In English, it's reaction kinetics in uniform supersonic flow to do kinetics at low temperature. And they also had a slit jet supersonic source in FTIR. Because Professor Jan Smith, some of you would know, has collaborated with Professor Rowe a lot. And Robert George, who was there, had the slit jet FTIR. Ludovic Bainier was working with CRUSU. He had experience in astrophysics. So when he wrote to me suggesting a collaboration, I agreed. It's been continuing. We had several visits exchanged from both sides. When I went to France, I had this paper, which was very popular, Rotational Spectrum and Structural Dynamics of Benzene Dimer. Bertrand Rowe and Ian Smith had looked at the association of benzene, the kinetics of benzene dimer formation. You take two benzene, they form a dimer. They did it because some mechanical engineer from Berkeley had proposed a soot formation stuff. And Bertrand Rowe didn't really agree. So that's why they started doing the experiments. Of course, not surprisingly, their experiments showed that beyond 70-80 Kelvin, the dimer isn't present at all. So they're just taking benzene plus benzene, benzene 2 and so on. So when I went to Brunn, I was asking Robert, why don't you do the infrared spectroscopy of benzene dimer? So what we showed was a T-shaped structure, which is a dipole moment, so we could study in microwave. Everybody talks about a parallel display structure that is invisible in microwave. But infrared absorption can be used to study both of them, and Robert could do. So we did the experiment. It took for almost 4 or 5 years because it started in 2005. We could not find the parallel display structure at all. And we were lucky to publish this in a first script for Powell Habza, who was the one who predicted the parallel display structure. As of today, there is no experimental evidence for this structure, but it continues to amuse theoreticians. So I was telling you, Bertrand Rowe did this because it's a mechanism proposed by Michael Frankla in the Mechanical Engineering Department of UC Berkeley. I realize many physicists and chemists are not working in this kind of areas, so the engineers end up doing the best they could. So what they said was, from benzene you remove hydrogen, add an acetylene. This is called Haka mechanism. You can form benzene to naphthalene to phenanthrene, anthracene, pyrene. This will explain the two-dimensional growth. After that, soot. And Bertrand was convinced this cannot happen because they are bound by van der Waals forces. Soot has chemical bonds, CC bonds. That's why he wrote to me. Now, discussing this, Ludovic came to our lab, we looked at the shock tubes and he was asking the opposite questions. Suppose we had only carbon and hydrogen, how did this hydrocarbon form? Can you investigate this? I said, of course we can do. Then he said, shock waves are very important in astrophysical settings. Remember, the Big Bang is probably the biggest shock ever produced. And shock waves are omnipresent, they are everywhere. This is protostellar outflows, ring nebula, Crab nebula, the shock wave. If you look at the molecular formation after the Big Bang, there are many theories like radiation, ionization, impact, collision. And Ludovic suggested shock waves could have played a role as well, because shock waves are there everywhere. He said, let's test it. So that's how we started. Of course, this is a cover article in PCCP. Again, starting from the carbon discharge, the temperatures, as someone was saying, is usually 10-20 Kelvin, but it can also be very large. We have this PAH. How dust is chemically and physically processed by shocks? What is the contribution of shocks to the dust life cycle? Could you identify some possible traces of interstellar shocks? SIO is supposedly interstellar shock, so we started working on this. Before I go on this is a simple introduction to the shock wave. Basically, the shock tubes are a high pressure side, low pressure side, separated by a diaphragm. You go on increasing the pressure, the diaphragm ruptures, produces a shock wave. It can increase the temperature and pressure. This is the primary shock. When it hits the end fall, it reflects. The reflex can further increase the temperature and pressure. When the diaphragm ruptures, there's an expansion fan created here which reflects back and quenches this. This is not like an ideal laser pulse, but this is like high temperature pulse. So we can have constant temperature and pressure for this dwell time. We call it typically of a millisecond. Heating is instantaneous. When I say instantaneous, it's like microsecond. Now, microsecond is an interesting period in chemistry because it's very long for thermal equilibrium. It's not femtosecond pulse. So you can really have thermal equilibrium. The cooling takes place over a few milliseconds. If you are looking at activated processes, they happen during this time. So shock tube, it turns out, is an ideal tool for testing transition state theory. You cannot do it with lasers. So we have a constant temperature and pressure. And of course, we had to make some changes to do this material shock tube. This is a recent picture again. We added one more section. We could keep a sample of solid and then expose this to the shock. Of course, now we can see the P1 lasts for longer because we have extended the tube, and this is not as clean as what I had before. But we know we have achieved some pressure and temperature for some time, and the solids have been processed by this. Then we would analyze what happens to them. So this is the laboratory astrophysics with shock tubes. We wanted to first look at C plus H2 reaction. We chose C60 as the source for C. We have also done experiments with diamond and graphite, many other experiments. So you would keep carbon here and H2 and argon here, helium here, and just blast it. We could get temperatures from 2000 to 6000 Kelvin, and then we analyzed the gases with GCMS, and also cavity ring down spectroscopy was brought by Samit Kasi from Grenoble. Of course, solid residues were analyzed with all this spectroscopic and microscopic techniques. I won't talk about much of them now. This is from the gas chromatography. We see mostly methane, ethane, ethylene, and acetylene. Some experiments we also noted benzene. And we did CRDS as well. Again, we could identify methane, acetylene, and ethylene. So this paper was published almost 10 years ago, 2016. So we could see this mostly methane and ethane, ethylene, acetylene kind of thing. We did not see any C3 hydrocarbons at that time. So I was wondering why there is no C3. Then of course we wanted to build a time resolved characteristic. Until now we were only analyzing the post-shock equilibrated products. We did not know any idea about what was happening during the time. Then we built a fast spectrometer that would allow us to measure C2 spectrum as a function of time. This is at approximately 5000 Kelvin. This is all C2 bands. We started with C60. Of course, this mechanism is very well known. So it detects a C2. There are plenty of C2. I was wondering, if we have so many C2, why isn't this reaction happening? C2 plus C2 giving C3 plus C. But we didn't find anything. In addition to the C2 features, we are seeing a broad background. It seems like a black body emission. So of course, we ordered more spectrometers. I can talk about this in more detail, but I don't want to spend too much time now. I welcome any of you in case you come to Bangalore, we'll be happy to show you this. Now we could really get the vibrational rotational distribution of C2 as a function of time. And of course, we've been analyzing this. We could see both reaction and relaxation, and we can fit them. Of course, then we thought maybe we should really look at these hydrocarbons. All these hydrocarbons are present in the interstellar space and also in combustion engines. So we chose coronium as the next example. So we did the experiment. This is some conditions. So we took coronium. We had 2500 to 4500 Kelvin, 20 to 30 bar. We are doing all this analysis. What was really interesting is when we looked at the spectrum, these are at different temperatures, we could assign all this swan band. What was surprising is when we had only C60, we had the C2 emission and a broad band, a black body radiation. But when you have coronium, we had the swan band, we had the black body radiation. In addition to this, we had to introduce one more peak centered around 540 nanometer. This was there. So we could clearly see three different sources of emission. One was just a black body radiation, one is C2, and then another peak. We're wondering what is this? We didn't see this when we had C60. But coronium, we are seeing it. So we did some more experiments. We ordered C60 and H2 and repeated the experiment. We just put ethylene and repeated the experiment. And we had repeated the experiment with fullerene without C2. These are the spectra we go. In ethylene, we see this peak in the green. In coronium, we see fullerene plus H2 we see. If you have only fullerene, we don't see this green emission. So it seems to be appearing only when there is carbon and hydrogen. Of course, we did some molecular dynamic simulation. It was predicting some CNH. In fact, C2H was very prominently predicted. So we looked at the spectra of C2H. This emission didn't overlap with what we found in the C2H. This must be some CNH. You know, how many of you noted? If you have to write a formula for soot, it's CNH. It's a lot of carbon and some amount of H. So this is the popular spectra, diffuse interstellar bands, and the infrared spectra. If you look at it, there are many bands, and what's really interesting is, if we can see this, there is one band at 545 nanometer, infrared spectra, unidentified IR band. Most of them are due to maybe fullerenes and carbon clusters, and this DIB has a 5450 nanometer angstrom, which is very close to what we found. Now, it's interesting, small carbon clusters were detected in astronomical sources. C, C2 and C3 are the prime components. These species are reaction intermediates. I think some of you may know, Croteau wanted to study these linear carbon chains. He could not study them because microspectroscopy cannot do that. He wrote to Smalley through Curl, who was a microspectroscopist. They just put a discharge on pencil to form linear carbon chains. And of course, they found fullerene and they got the Nobel Prize. But what's really interesting, fullerene has been found in space now. So nobody was looking for fullerene. They found, and it's been found in space. But I was always worried about this. Examples of soot formation, hot flames, diamond synthesis, gas phase pyrolysis, formation and decay of fluorine, everywhere you have the C and C2. So, what about this reaction C2 plus C2 giving C3 plus C? How many more minutes I have? Yeah. Good, that's perfect. So, I thought this reaction someone should investigate because C2 is there everywhere. In combustion, we are studying combustion, OH emission, C2, CH. These are the species that are found. Interstellar space, you see them. And this reaction is important, but nobody seems to have done any work on this. Maybe I should correct myself. Paul Roth did some experiments in a shock tube. They did see C, C2 and C3. They had some mechanism. They just wrote C2 plus C2 giving C plus C3. And they just fitted this data. When we went through this pieces, this paper, C2 emission is from the excited triplet states, not from the ground state. The swan band is the triplet emission. The ground state is singlet. And of course, Paul Roth is also in a mechanical engineering department. So they were observing C, C2 and C3. They did not worry about what spin states they were. Of course, one good thing or bad thing about kinetics is you can always write a mechanism and fit the concentration profile. And they agree and they publish. If you remember the first quote I had about kinetics, that's fascinating. It's a strong formation of both C and C3. They did see C3. C2 decreases with equilibrium. They just concluded this is the equation. They put octave energy as 0 Kel for this. This didn't make sense to me. So I had an integrated PhD student with me. I told him, you do this as an MSc project. I had no idea how complicated this reaction will turn out to be. Will it really form C3 or not? Now, if you remember Philip's talk, he said C4 has not been found in interstellar space. We have C2, C3, C5, C6, no C4. We thought we should investigate this in detail. But of course, if you look at C2, ground state is X, singular sigma G plus, excited is triplet per U. The energy difference is only 2 kilocalorie per mole. You look at C3, C3 can even have different structures. The linear structure has singular sigma and also a triplet per U. It can also have a cyclic structure. Cyclic structure also has triplet A2 prime. I think it's from the grade. This is from paper by Whitesides. So we have linear and cyclic, both having different electronic states. The relative energy difference between linear and cyclic is about 24 kilocalorie per mole. If you go to C4, it has 3 possible structures: linear, this and this rhombic. And all these structures have different spin states. So we did the best we could do, MRCA, CCSD, cos SCF, cos P2, whatever we could do. C3 monocyclic is singlet ground state, 30 kilocalorie per mole, to almost isoenergetic isomers. So this is not a simple reaction. And C4 has linear, again it has a triplet and singlet state. It has a rhombic structure which has a singlet ground state and triplet excited state. You can, of course, if you have looked at C, C2 and C3, you write a chemical kinetics mechanism and you fit the data. But if you look at the complication, I wish some chemist had looked at it. Now, how many of you remember Josh Schwartz talked about some simple autoionization reaction? That's based on Ron Hansen's shock tube experiments from Stanford. We need serious physical chemists to investigate this. I am not an excellent theoretical chemist, but somehow we touched this. So we wrote down a mechanism. C2 plus C2, of course. I worked with Setzer, so I know addition elimination reactions. It could actually form C4. C4 can give C3 plus C. It can isomerize. It can go back to C2 plus C2. It can go to cyclic C3 plus C. So we wrote down this broad mechanism, and of course all of them have the different electronic states. So we calculated the barrier for each one of them. We did scanning. We found it's not a simple reaction. These are all some numbers we had. So we spent, in fact, several years doing all of them. The numbers are not important. Finally, with the simulation, we found out Paul Roth and his colleagues have made some assumptions that were not needed because of thermochemistry. We could really fit the same data, but when you look at the C2 emission, we are only calculating the C2 triplet concentration here, not the total concentration. That's what we are measuring. I mean, they have measured. So we could really explain this result, including all the spin states, structural diversity, everything. I thought we have done a lot of work. We could publish this. Because we did submit this to JPC. And of course, I think David Osborne was there. He said, you need to worry about spin orbit coupling. Without that, you cannot do this. I know we have to worry about spin orbit coupling. Our calculation is basically assume thermal equilibrium. It is not trivial. So then I, of course, contacted Lourdes. He is helping us now. I hope we can do the dynamics, including spin orbit coupling. That's almost the end of my talk. It's a brief summary. C2 plus C2, C3 plus C is not a barrierless reaction. It's unlikely that it's a one-step reaction. Less than 500 Kelvin temperature and high pressure, C4 is mainly formed by addition of C2. At lower pressure, C4 is not formed, perhaps explaining the lack of observation in interstellar medium. The pressure is low, C4 just doesn't form at all. At temperatures more than 500 Kelvin, C2 is mainly formed at singlet surface, whereas C3 plus C formed at triplet surface. So depending on the spin state of the electronic state, you would either have C3 plus C or just go back to C2. This reaction is sensitive to spin states of C2 as well as the temperature and pressure. C2 is only monitored in the triplet surface, but they have been just writing it as C2. Formation of cyclic carbon species are negligible in our calculation. It's a final conclusion because as I told you, singlet shock tube is a fantastic tool to compare transition state theory because you have a well-defined temperature and microsecond time is long enough for thermal equilibrium but short enough for reaction kinetics. I did build a mass spectrometer to look at shock emission. Our experiment is Coronin has shown some emission at 545 nanometer in addition to C2 swan bands and the black body emission. And we are convinced that this is from some CNH and this could be the source for the DIB emission at lambda 5450. C2 plus C2 reaction deserves all efforts from serious theoreticians, not me, and of course experimentalists. As of now, it seems like radical reaction are too difficult for anyone in the world. I hope it changes. Remember Josh's talks on associative ionization and hypersonic flow, of course, Marcus was also talking about it. Hypersonics is an extremely important field. And I'm glad our lab was the first to do that in India. Because we have a Center for Hypersonics, Center for Excellence in
Swayam Prabha. Digital India. Educated India.